Let's start here. This frame is from December 19th. Pulled lit from Chuck's astrophotography using Starfront's 24-inch telescope. At first glance, it looks quiet, a compact glow, soft envelope, nothing dramatic. But look closer at the geometry. The central region stays tight and well-defined, while the surrounding haze stretches unevenly in one direction. It isn't blooming symmetrically. It isn't smearing with the stars. The object is holding its shape while the background tells you the mount is doing exactly what it should. This matters because large apertures don't forgive mistakes. A 24-inch system amplifies tracking errors, seeing issues, and processing artifacts. If something shows up cleanly here, it's not accidental. What we're seeing is a persistent directionally biased structure, already familiar from smaller scopes, now confirmed again at much higher resolving power. This is our baseline. Now let's move image by image and see what changes and, more importantly, what doesn't. Now let's move to this one. This image comes from December 19th, captured by Ivan Vasquez at Calopa Stars using a C-Star S50, a much smaller consumer-grade system compared to the 24 and we just saw. And that contrast is the point. Despite the shorter 20-minute stack of 10-second exposures, the object doesn't dissolve into noise. The core stays compact. The surrounding glow isn't circular. It stretches subtly in the same general direction we just saw in the larger telescope data. Notice what isn't happening here. The stars remain round. There's no smearing from bad tracking. No aggressive processing pulling shapes out of nothing. Yet, the object itself still shows an elongated inner structure even at this scale. This matters because small scopes are unforgiving in a different way. If a feature survives limited exposure time and modest optics, it's not something that only appears under extreme processing or large apertures. What we're seeing is scale-independent behavior. Large telescope, small telescope, same story. Let's keep going. Now look at this follow-up frame from the same observer. This is a 15 to 16-minute stack still from the C-Star S50 taken later. The same night on December 19th. With more integration time, something important happens. The object doesn't just get brighter, it gets more defined. You can clearly see the inner region stretch into a narrow, elongated shape, with a brighter condensation at one end, and a softer extension trailing away from it. The surrounding glow isn't symmetric. It has a preferred axis. Meanwhile, the background stars tell a different story. They stay around. They don't smear. They don't stretch in the same direction. That rules out wind shake, bad tracking, or stacking errors. What this frame adds is temporal reinforcement. Same instrument, same night, longer exposure, same orientation. If this were noise or processing illusion, longer stacking would blur it out. Instead, it sharpens. That's the pattern we keep seeing. Let's move on. Now, we jump to Italy. This image comes from Tony Scarrato, captured on December 18th using a 25cm Newtonian telescope. This isn't casual imaging. It's a long, carefully stacked sequence with known resolution, pixel scale, and field orientation. First, look at the raw wide field. The background stars are stir. That tells you the telescope is tracking the object itself, not the sky. And right at the center, 3i Atlas stays tight. Now, compare that to the resampled close-up on the right. The inner coma is no longer circular. It's elongated with a clear axis running at roughly PA, approximately 110. That's a specific measurable direction, not a vague blur. The central condensation is sharply defined around it. The outer coma expands into a broad greenish envelope estimated at hundreds of thousands of kilom across. What matters here isn't just the shape, it's the structure within the shape. You have a compact central core, an elongated inner region, a larger asymmetric outer coma. That's a layered system. And once again, the elongation lines up with what we've already seen from smaller instruments, from different continents on different nights, different telescope, different processing, same directional behavior. That consistency is doing the heavy lifting here. Let's keep going. Now we move to New Zealand. This frame was captured by Brian Dietrich on December 17th using a 203mm Schmidt-Cassatt grain. Short exposures, minimal processing, clean tracking. At first glance, it looks quiet. A faint object, no dramatic flare, no obvious tail jumping out. But that's the point. The central condensation stays compact. No smearing, no breakup. And the surrounding glow isn't random. It's slightly biased in one direction. Now look at the inset. This is a stretch of the same data. Nothing added, nothing painted in. And again, the inner structure doesn't collapse into noise. It holds together. Here's why this matters. When an object is this faint, processing artifacts usually dominate, edges wobble, centers wander, shapes dissolve. That doesn't happen here. Instead, the core remains locked in place while the surrounding material shows the same preferred orientation we've already seen from Italy and Hawaii. Different hemisphere, different telescope, different night, same behavior. By this point, the pattern isn't coming from one setup or one observer. It's coming from the object. Let's keep stacking the evidence. Now we step off Earth entirely. This image wasn't taken by an amateur telescope or even a ground-based observatory. It comes from NASA's Europa Clipper spacecraft using its ultraviolet spectrograph, captured on November 6th from roughly 164 million kilometers away. What you're looking at here isn't a photograph in the usual sense. It's a composite intensity map, plotted in ecliptic longitude and latitude showing where ultraviolet emission is concentrated. As the instrument scanned across the sky, that bright blue region, that's 3I Atlas. Notice something important. The emission isn't spherical. It isn't symmetric. It's elongated along a preferred direction embedded within a broader diffuse structure, even at ultraviolet wavelengths, even from interplanetary space, even with a completely different observing method. The geometry holds. This matters because UV instruments don't care about dust tails or pretty optics. They respond to gas, excitation, and interaction with solar radiation. So, when a directional structure shows up here, it's not a camera artifact. It's not a stacking trick. It's not contrast abuse. It's physical. By this point, we have the same orientation appearing in raw optical frames, RGB channel separations, long-time series stacks, and now ultraviolet spectroscopy from a spacecraft millions of kilometers away. Different physics, same alignment. That's no longer coincidence. It's behavior. And whatever is driving it is still active. So here's where we land. Across different nights, different telescopes, different continents, and even a spacecraft, 3I Atlas keeps showing the same thing. A compact core and a directional structure that refuses to fade, rotate randomly, or break apart. This isn't coming from one observer. It isn't coming from one filter. And it isn't appearing only after heavy processing. Whatever is driving this, behavior is stable, persistent, and real. The question now isn't whether the structure exists. It's why it's holding together this cleanly and why it's showing up so clearly right now. Is this a jet driven by localized activity, a geometry effect we're catching at the perfect angle, or something about interstellar material behaving differently than we expect? Drop your thoughts in the comments, and if you want the next update, the moment new images arrive, like the video, subscribe, and share this with someone who's been following the 3I Atlas story. We're not done with this object.